Dogs. Most people grow up thinking dogs live in a gray, colorless world. That is not quite true, but the reality is still pretty far from what we experience. Dogs have only 2 types of color receptors instead of 3, which means the rich spectrum of colors we see gets compressed into a narrower palette of blues and yellows. A bright red toy sitting on green grass just looks like a brownish blob against a brownish background to them. But here is what makes dogs remarkable. Their eyes were never built for color. They were built for survival. Their vision is wired to catch the tiniest flicker of movement, even in near total darkness. A dog might walk right past a red ball lying still, then snap to attention the instant it rolls an inch. Their world is less colorful than ours, but it is faster, sharper in the dark, and tuned to motion in a way ours simply is not. Cats. If dogs are built for motion, cats are built for the dark. Anyone who has owned a cat knows they come alive after midnight, and their eyes are a huge reason why. Behind the retina, cats have a special reflective layer called the tapetum lucidum. Think of it like a mirror sitting at the back of the eye. Light enters, the photoreceptors try to catch it, and whatever slips through gets bounced back for a second attempt. This is why cat eyes glow in photographs, and why even a sliver of moonlight is enough for a cat to navigate a room perfectly. The strange trade-off is that in bright daylight, cats actually see the world more blurry and washed out than we do. They are not impressed by the vivid afternoon. They are saving their best vision for the hunt that happens after the sun goes down. Eagles. There is a reason the eagle became the symbol of precision, power, and sharp judgment across so many cultures throughout history. An eagle soaring thousands of feet in the air can spot a small rabbit moving through a field nearly 2 miles below. That is not an exaggeration. Their eyes are packed with almost 5 times more photoreceptors per square millimeter than human eyes, despite being roughly the same physical size. But what truly sets them apart is something called a dual fovea. Humans have 1 fovea in each eye, a tiny zone of crystal clear focus. Eagles have 2. This means they can lock onto a target in the distance while simultaneously keeping full awareness of what is happening to the side. They are not choosing between focus and awareness. They have both at the same time, always. Bees. Here is something worth sitting with. Every garden you have ever walked through looked completely different to the bees flying around you. Bees cannot see red at all. To them, a vivid red rose appears as a dark, almost black shape. But they see something we cannot: ultraviolet light. And flowers have known this for millions of years. Many plants have evolved ultraviolet patterns on their petals, invisible to us, that act almost like neon signs pointing straight toward the nectar. A flower that looks plain white to a human eye might be covered in bold, swirling UV patterns to a bee, essentially screaming out directions. The entire relationship between flowering plants and bee pollination was built on a visual conversation happening at a frequency we have never been able to see. Mantis shrimp. No creature gets more attention in conversations about animal vision than the mantis shrimp, and it genuinely deserves the spotlight. While humans process color through 3 types of receptors, the mantis shrimp has 16. For years, scientists imagined this meant they were experiencing something like a psychedelic explosion of color beyond anything we could comprehend. The truth that emerged from deeper research is actually even more interesting. Mantis shrimp do not seem to blend and compare colors the way we do. Instead, they appear to identify specific wavelengths almost like reading a barcode. Rapid, precise recognition without the processing overhead of mixing and comparing. Their visual system is not built for experiencing color richly. It is built for classifying it instantly. This makes perfect sense for an animal that strikes prey with the speed and force of a bullet. There is no time to appreciate the view. There is only time to act. Snakes. Certain snakes do not just see the world, they feel it with their eyes. Pit vipers, pythons, and boa constrictors have special organs near their mouths that detect infrared radiation, meaning they sense heat rather than light. In total darkness, with 0 visible light entering the room, a snake can still build a detailed enough picture of its surroundings to strike with accuracy. Warm-blooded animals, mice, birds, small mammals, glow against the cooler background like a lit candle in a dark room. What makes this even stranger is that this heat-sensing system is entirely separate from their regular vision. These snakes are essentially running 2 different visual feeds at once, one built from light and one built from thermal energy, and combining them into a single hunting advantage that works around the clock. Horses. A horse does not need to turn its head to see you walk up behind it. Their eyes sit on the sides of their skulls, giving them a field of view that wraps around to nearly 350 degrees, almost a complete circle. This is the vision of an animal that evolved not as a predator, but as prey, always watching, always listening, always aware that something might be coming from any direction. The cost of this wide-angle awareness is depth perception. The zone where both eyes overlap and allow a horse to judge distance is relatively small, sitting in a narrow band directly in front of their face. Horses do not need to know exactly how far away the predator is. They need to know it is there at all, and they need to know immediately. Their entire visual system is a survival machine, optimized for one job: do not get caught off guard. Flies. Swatting a fly and missing is not just embarrassing, it is actually a fair fight. A housefly's compound eyes are built from thousands of tiny individual lenses, each one aimed at a slightly different angle, creating a wide mosaic view of the world all at once. But the real reason flies are so difficult to catch has less to do with their field of view and more to do with how fast they process what they see. Flies experience time differently. Their visual system refreshes so rapidly that what looks like a smooth, continuous movement to us appears more like a slow, frame-by-frame sequence to them. Your hand moving toward a fly is, from its perspective, arriving in something close to slow motion. It sees the threat building, calculates its exit, and is already gone before your palm gets close. You were never as fast as you thought. Reindeer. In the deep Arctic, winter brings nearly total darkness for months at a time. Most animals struggle. Reindeer adapted. They are the only known mammals whose eyes physically change with the seasons. In summer, the reflective layer at the back of their eye glows golden, optimized for bright light. As winter arrives and darkness takes over, that same layer shifts its structure and turns blue. And in doing so, it begins letting ultraviolet light through. This matters enormously because under UV light, things that are invisible in ordinary conditions suddenly stand out. Urine trails left by predators glow. Patches of lichen buried under snow absorb UV and appear as dark patches against a bright background. Polar bear fur, white and camouflage to us, absorbs UV and shows up clearly. Reindeer do not just survive the Arctic winter, they have a visual system that was rebuilt by evolution specifically to read it. Cuttlefish. The cuttlefish sits at the center of one of the most fascinating unsolved puzzles in animal biology. They are completely colorblind in any conventional sense. They have just one type of color receptor, which by all logic means they should see the world in shades of gray. And yet, they are among the most sophisticated color changers on the planet, capable of matching the exact hues, textures, and patterns of coral, sand, and rock in fractions of a second. How does an animal that cannot see color produce camouflage that is perfectly color-matched? The most compelling theory points to their extraordinary W-shaped pupils. That strange shape may allow them to exploit chromatic aberration, a phenomenon where different wavelengths of light naturally focus at slightly different depths inside the eye. By subtly adjusting focus, a cuttlefish might be able to identify colors not by comparing receptor signals, but by detecting tiny focus differences. They may have found a completely different solution to a problem that should have been impossible to solve.